Sunlight hitting your face looks blindingly white, but that white is actually an optical illusion. It contains the entire visible color spectrum, bursting apart into the familiar reds, greens, and blues of a rainbow only when forced through a prism. Incoming sunlight navigates Earth's atmosphere, a dense, microscopic obstacle course packed with nitrogen and oxygen molecules. When incoming sunlight crashes into this gas wall, the collision triggers a process called Rayleigh scattering. The light splinters and bounces in every direction, following a strict rule based entirely on shape. Light travels in waves, and the length of those waves dictate how they behave. Long, lazy red waves easily slip past the microscopic gas molecules untouched. Blue waves, however, are short and tightly packed. They plow directly into the gas molecules and splinter outward. Because these short blue waves relentlessly ricochet across the upper atmosphere, they saturate the air above us, creating the blue canopy we see every day. We accept this logic as the complete story, yet a closer look reveals a massive hole in this textbook explanation. This graph compares visible light wavelengths. Violet light is measurably shorter, tighter, and vibrates faster than blue light. If shorter waves scatter more aggressively, Rayleigh scattering mechanics demand violet dominate our atmosphere. Mathematically, the sky should be brilliant violet. This mathematical discrepancy proves the standard physics of scattering is incomplete. A hidden combination of forces is masking the violet reality from our eyes. Solving the mystery requires tracing the light back 93 million miles to its exact point of origin, the sun. It is easy to assume that a star pumps out a perfectly balanced rainbow, producing reds, greens, blues, and violets in equal amounts. The reality of solar physics is much more lopsided. This chart of the sun's solar radiation spectrum shows a massive quantitative peak right over the blue wavelengths, followed by a sharp, dramatic drop-off when it gets to the violet section. Earth's atmospheric molecules scatter the raw material they are given, a mixture that arrives at our planet already dominated by blue wavelengths. Our sky isn't violet, partly because our host star is a poor manufacturer of violet light. The final reason those scattered violet waves vanish from our perspective lies within the evolutionary limits of human anatomy. At the back of the eye, the retina relies on millions of microscopic cone-shaped cells to interpret color data. Human vision evolved to be hypersensitive to blue light. Our eyes act as biological amplifiers, taking the abundant blue light in the sky and turning the perceived volume all the way up. This sensitivity curve chart illustrates a rapid plunge down to near zero over the violet spectrum. We possess a biological blind spot for those wavelengths, essentially ignoring them even as they strike our retinas. The blue sky is an illusion created by the combined biases of a blue-heavy star and a blue-sensitive human retina. This delicate balance of physics and biology drastically changes every single evening as the sun approaches the distant horizon. As Earth rotates, setting sunlight travels horizontally through a much thicker slice of atmosphere. Short blue waves scatter violently and fade away long before reaching us. Only the long red and orange waves bypass these obstacles to reach the surface. These blazing red sunsets are the visual remains of a sunbeam after thousands of miles of atmosphere strip the blue away. The sky itself is a completely transparent void, possessing no inherent pigment or color. Every shift from deep blue to burnt orange is the visible result of precise mathematical collisions. Every glance at the sky is a front-row seat to a real-time dynamic filter, balancing solar radiation, atmospheric fluid dynamics,